Close your eyes for just a moment. Picture this: an explosion of energy so vast, so unimaginably powerful, it gave birth to everything you've ever known. Stars, galaxies, even the atoms in your body, all of it traces back to a single, fleeting instant, the Big Bang. But what if I told you that the most crucial moment in our universe's story wasn't the explosion itself, but what came immediately after? A sliver of time so short, it defies comprehension, just 1/trillionth of a second. This is the Planck Epoch, the universe's first heartbeat, where the very fabric of reality was woven. And today, we're going to step into that moment to uncover the secrets hidden in that infinitesimal blink of existence. Why does this matter? Because in that fleeting trillionth of a second, the rules of physics as we know them didn't exist. Gravity, light, even time itself, they were all born here in this chaotic, unfathomable dawn. This isn't just ancient history, it's the foundation of everything. The Planck Epoch holds the answers to questions we're still asking today. Why is our universe made of matter and not antimatter? What existed before time began? And could there be other universes hidden in dimensions we can't yet see? These aren't just abstract ideas, they're the keys to understanding our very existence. Think of it like this: the Planck Epoch is the universe's first brushstroke on an empty canvas. Every galaxy, every planet, every life form that followed was shaped by the decisions made in that instant. And yet, despite its importance, this era remains one of the greatest mysteries in science. We're peering back over 13.8 billion years, trying to decode a moment that lasted less than the blink of an eye. But with cutting-edge theories and breakthroughs in quantum physics, we're closer than ever to unraveling its secrets. So, if you've ever looked up at the night sky and wondered how it all began, you're in the right place. This is the story of the first trillionth of a second, and it's more astonishing than anything you've imagined. To grasp the Planck Epoch, you first have to understand just how unimaginably brief it was. We're talking about a span of time so short, it makes a nanosecond feel like an eternity. Just 10 to the power of negative 43 seconds. That's a decimal point followed by 42 zeros and then a 1. If you tried to count to that number, you'd never finish because the entire lifetime of our universe wouldn't be long enough. But in that sliver of existence, everything we know about physics was turned upside down. This was the universe at its most extreme, a seething cauldron of energy where temperatures soared beyond 10 to the power of 32 degrees. That's so hot, even the cores of the hottest stars today would feel icy in comparison. Matter as we know it couldn't exist here. Atoms, they wouldn't form for billions of years. Even the fundamental forces, gravity, electromagnetism, the strong and weak nuclear forces were still fused together into a single, unified superforce. It's like taking all the rules of nature, throwing them into a blender, and hitting a speed we can't even measure. What makes this era so fascinating and so frustrating for scientists is that our current laws of physics simply don't apply here. Einstein's relativity, useless; quantum mechanics, incomplete. The Planck Epoch exists in a realm where space and time themselves were still flickering into existence, twisting in ways we can't yet describe. This is where the real mystery lies. If we could unlock the secrets of this moment, we might finally understand how the universe went from pure chaos to the structured cosmos we see today. Imagine trying to solve a puzzle where the pieces keep changing shape. That's the challenge physicists face when studying this era. The clues are written in the fabric of reality itself, in the way galaxies spin, in the faint echoes of cosmic background radiation, but the full picture remains just out of reach. Yet every breakthrough, from superstring theory to loop quantum gravity, brings us a little closer to peering back into that first trillionth of a second. And what we find there could rewrite not just the story of our universe, but the very laws that govern it. The Big Bang wasn't just an explosion, it was the unfolding of reality itself, and the Planck Epoch was its opening act. While we often picture the birth of the universe as a fiery burst of matter and energy, that dramatic scene came later. In those first indescribable moments, there were no stars, no particles, not even space and time as we experience them today. Instead, the Planck Epoch was a realm of pure potential, where the seeds of everything from the forces that govern atoms to the vast cosmic web of galaxies were planted. Scientists obsess over this fleeting instant precisely because it was so transformative. Imagine baking a cake. The final product depends entirely on those first critical seconds when ingredients blend, even if the mixing seems insignificant compared to the hours of baking. Similarly, the Planck Epoch was the universe's mixing phase. The way energy fluctuated, the way spacetime itself began stretching. These microscopic quirks determined whether galaxies would cluster or scatter, whether matter would dominate antimatter, even whether life could eventually emerge. Miss one subtlety in that first trillionth of a second, and our universe might have collapsed instantly or stretched into an empty void. But why can't we just skip ahead to the more familiar parts of the Big Bang? Because the Planck Epoch holds the cosmic blueprints. The conditions we observe today, the precise strength of gravity, the number of dimensions, even the way light travels, were likely locked in during this era. It's like trying to understand a tree by only examining its leaves without ever studying the roots. Without grasping the Planck Epoch, we're left with half the story, forced to theorize about effects without knowing their causes. This is where Einstein's vision collides with quantum weirdness. For decades, physicists have struggled to reconcile the vast, predictable cosmos described by relativity with the chaotic, probabilistic world of quantum particles. Yet in the Planck Epoch, these two seemingly opposite frameworks had to coexist, or perhaps they were one and the same. Some theories suggest that during this time, gravity behaved like just another quantum force, flipping our modern understanding on its head. If true, it would mean the universe didn't just evolve, it remembered its earliest state, carrying traces of that unified superforce into the present. The Planck Epoch's brevity makes it a tantalizing puzzle. Like catching a single frame from a high-speed film, we're left with fragments equations that break down at these energies, ghostly signals in cosmic radiation, mathematical hints of extra dimensions. But each clue suggests something extraordinary, that our universe wasn't just born in the Big Bang, but designed in the Planck Epoch. Every law of physics, every constant that makes reality stable enough for atoms and us to exist might trace back to decisions made in that unfathomably short flash. And that's why scientists keep searching, because buried in those first moments might be the answer to the ultimate question: why is there something rather than nothing? Right now, you can lift your phone, feel the warmth of sunlight on your skin, even watch electrons dance in a lightning bolt, all because nature operates under four distinct forces. But rewind to the Planck Epoch, and that tidy division didn't exist. Gravity, electromagnetism, and the nuclear forces weren't separate players. They were one and the same, merged into a primordial superforce so powerful, it makes today's physics look like a simplified sketch. Picture a time before labels, before categories, when the universe was too hot, too dense for any distinctions to hold. At temperatures exceeding 10 to the power of 32 degrees, particles didn't just collide, they lost their identities entirely. The gentle pull of gravity and the crackle of electromagnetism were indistinguishable, woven together like threads in a single cosmic tapestry. Even the strong nuclear force, the glue holding atomic nuclei together, and its weaker counterpart were part of this unified whole. It's as if you took the entire periodic table and compressed it back into a single elemental ingredient. Why do physicists believe such a merger happened? The math demands it. Just as ice melts into water under heat, our equations show that at extreme energies, the forces we observe today must converge. Think of it like tuning a radio. At one frequency, you hear static, at another, a clear signal. The Planck Epoch was the universe's highest energy frequency, where all forces blurred into a single harmonic. Yet proving this isn't just about equations, it's about glimpsing a reality far beyond our experimental reach. Here's the catch: we've never directly observed this unification. Particle accelerators like the Large Hadron Collider can't yet recreate Planck-scale energies. They'd need to be a trillion times more powerful. So scientists rely on clues like cosmic inflations imprint on the microwave background or subtle symmetries in particle behavior. Some theories, like string theory, suggest extra dimensions could explain how forces split apart as the universe cooled. Others propose that gravity's quantum form, still undiscovered, held the key. What's at stake? Everything. If we could decode that superforce, we'd unlock why electromagnetism is perfectly tuned for chemistry, why gravity is inexplicably weak compared to other forces, even why time flows in one direction. It's not just about rewriting textbooks, it's about discovering the universe's first rule book, written in a language we're still learning to read. And somewhere in that chaos of unified forces lies the answer to how nothing became everything, all within that first trillionth of a second. At the heart of the Planck Epoch lies a puzzle so profound, it has stumped the greatest minds for decades: quantum gravity. We know how gravity works on cosmic scales, bending galaxies and sculpting the universe. We've mapped the quantum realm where particles flicker in and out of existence, but merge these two worlds, that's where physics hits a wall. And until we crack this code, the Planck Epoch remains a locked door. This is where Planck units enter the story. Named after physicist Max Planck, these are the universe's natural measuring sticks, the smallest possible slices of space, time, and mass. Take Planck length, about 10 to the power of -35 meters. That's so tiny, if you enlarged an atom to the size of the observable universe, a Planck length would still be smaller than a single grain of sand. Or Planck time, the interval it takes light to cross that infinitesimal distance. These aren't just abstract numbers, they're the thresholds where gravity and quantum mechanics collide. Why do these scales matter? Because below them, our physics breaks down entirely. Imagine zooming in on a digital photo until you see individual pixels. Go further and the image dissolves into meaningless noise. The Planck scale is that limit for reality itself. At these extremes, spacetime isn't smooth and continuous like Einstein described. It's thought to froth with quantum bubbles flickering in and out of existence. Gravity, usually a gentle curvature, becomes a chaotic storm. The quest for quantum gravity is like trying to invent a language for a place where words fail. String theory suggests tiny vibrating strands might bridge the gap. Loop quantum gravity proposes spacetime is woven from interlocking rings, yet both remain unproven. Even black holes, those cosmic laboratories where gravity reigns supreme, offer only cryptic hints. When matter crushes into a singularity, does it vanish? Or rebound at the Planck scale? We don't know, because at that moment, relativity and quantum mechanics scream in contradiction. Here's the breathtaking part. The Planck Epoch wasn't just a stage for these extreme conditions, it was these conditions. For that trillionth of a second, the entire universe existed at Planck scales, which means if we ever unravel quantum gravity, we wouldn't just solve a textbook problem. We'd glimpse reality's blueprint, the rules written when all forces, all dimensions, and all possibilities existed as one. And that's why this isn't just physics. It's archaeology at the edge of existence. String theory dares to answer the impossible. What if all the chaos of the Planck Epoch wasn't chaos at all, but a symphony? Imagine the universe's tiniest building blocks aren't point-like particles, but shimmering threads, vibrating at different frequencies like the strings of a cosmic violin. The pitch of each vibration determines whether it becomes an electron, a quark, or even a carrier of gravity itself. It's an elegant idea, one fundamental ingredient, countless possibilities. But why does this matter for the Planck epoch? Because string theory doesn't just unify particles, it weaves space and time into the fabric of reality. In those first moments when all forces were one, strings may have danced in 10 or 11 dimensions, far beyond the 3 we experience daily. Some dimensions could have curled into loops smaller than atoms, hidden from view. Others might have stretched into cosmic landscapes we'll never perceive. This isn't science fiction, it's math with startling implications, the theory's boldest promise. A true theory of everything. While the standard model explains particles and forces and relativity handles gravity, they speak different languages. String theory whispers that both are chapters in the same book written in the Planck epoch. Picture a frozen lake cracking under thaw. The fractures seem separate, but beneath the ice they're all connected. Similarly, strings could explain why gravity is so weak it leaks into extra dimensions, or why matter dominates antimatter, a subtle asymmetry in string vibrations. Critics argue string theory is untestable for now. Without particle accelerators the size of solar systems, we can't probe Planck-scale energies directly. Yet mathematical beauty keeps drawing physicists in. Like detectives reconstructing a crime scene from a single fingerprint, they hunt for indirect clues, echoes of extra dimensions in gravitational waves or tiny stringy effects in quantum experiments. The stakes couldn't be higher. If strings existed in the Planck epoch, they didn't just shape the early universe, they are the universe. Every star, every human, every law of physics might be notes in a melody started 13.8 billion years ago. And that's the haunting allure of string theory. It turns the Big Bang's cacophony into a song we're only beginning to hear. If the Planck epoch was the universe's first breath, cosmic inflation was its first sprint, a growth spurt so violent it stretched space itself faster than light. Within a fraction of a second after that initial trillionth, the cosmos ballooned from smaller than an atom to something approaching grapefruit size. That might not sound impressive until you realize this expansion wasn't just fast, it was exponential, doubling in scale at least 60 times over. And here's the twist, this runaway growth wasn't random. It was the universe's direct response to the extreme conditions forged during the Planck epoch. Inflation theory bridges two seemingly disconnected worlds, the quantum chaos of the Planck era and the orderly cosmos we see today. Picture a pot of water boiling violently on a stove. The Planck epoch was that rolling boil where quantum fluctuations made spacetime shudder like steam bubbles. Then, as the universe cooled slightly, it triggered inflation, like flipping a switch that turned boiling water into a geyser. Energy trapped in the fabric of space itself got repurposed as an unstoppable stretching force, smoothing out wrinkles and locking in quantum jitters as cosmic blueprints. This explains one of cosmology's biggest headaches, the horizon problem. Look in opposite directions of the night sky, and you'll find nearly identical temperatures in the cosmic microwave background, down to 1 part in 100,000. But without inflation, these regions could never have exchanged heat. Light wouldn't have had time to travel between them since the Big Bang. It's like finding 2 cups of coffee in different cities at exactly 72.3 degrees without anyone coordinating. Inflation solves this by revealing those patches were once neighbors, crammed together in the Planck epoch's microscopic playground before being wrenched apart. The fingerprints of this process are everywhere. Quantum fluctuations from the Planck scale, those tiny spacetime shivers, got stretched into cosmic proportions during inflation, becoming the seeds for galaxies. That's why the universe isn't a featureless void. The imperfections we see today were literally baked in when the universe was smaller than a quark. Some theories even suggest inflation wasn't a one-time event. The same quantum fields that drove it could have created a multiverse, countless bubble universes, each with different physics spinning off eternally. Yet inflation's brilliance raises new questions. What stopped it? Most models point to a sudden energy release like a cosmic deflation. that converted inflationary energy into the hot soup of particles we call the Big Bang. But the exact trigger remains elusive. It's as if we've found footprints leading away from the Planck Epoch, but the path is still half buried. What's certain is this: without inflation's explosive expansion, the universe might have remained a dense, chaotic speck. Instead, it became a stage vast enough for stars, planets, and life, all because of decisions made in those first fleeting moments. At the Big Bang's very beginning, our equations hit a wall, a singularity where density and temperature spiral into infinity, a point where the laws of physics simply stop making sense. It's like zooming in on a calculator screen until the numbers overflow into error messages. But here's the catch: singularities aren't physical. They're mathematical red flags screaming that we're missing a piece of the puzzle. And that missing piece, it's almost certainly hidden in the Planck Epoch. For decades, scientists accepted the singularity as an unavoidable starting point, a cosmic, here be dragons, on the map of the early universe. But the Planck Epoch offers a way out, a realm where quantum gravity might have smoothed those infinities into something real. Picture a movie played in reverse. As galaxies collapse toward the Big Bang, classical physics predicts everything condenses into an infinitely tiny, dense point. Yet quantum mechanics suggests a different ending. At scales smaller than a Planck length, spacetime itself might stop being continuous, instead becoming grainy or foamy. This quantum texture could act like a safety net, preventing true infinity by breaking reality into discrete, indivisible chunks. The clues lie in black holes, cosmic laboratories where gravity runs wild. Just as the Big Bang singularity defies explanation, so do the singularities at the hearts of black holes. But recent breakthroughs in quantum gravity hint that black holes might not crush matter into infinity after all. Instead, Planck scale effects could cause collapsing stars to rebound or transform into exotic objects like wormholes. If true, the same physics might apply to the Big Bang, replacing its mythical singularity with a quantum bounce or a transition from a previous universe. String theory and loop quantum gravity both offer ways to sidestep the singularity problem. Strings, with their vibrating dimensions, could blur the sharp edges of infinity. Loop quantum gravity's woven spacetime might resist collapsing to zero size. Even the holographic principle, the idea that our three-dimensional universe is a projection of two-dimensional information, suggests singularities are illusions, like mirages in a cosmic desert. The stakes couldn't be higher. If the Planck Epoch holds the key to resolving singularities, it doesn't just rewrite the first chapter of the universe, it redefines what's possible. Did time truly begin at the Big Bang, or was there a before? Could other universes have left imprints in ours? These aren't just philosophical musings. The answers could determine whether our cosmos is one of many in an endless cycle, or a solitary flare in an eternal void. And that's why the Planck Epoch isn't just about the past, it's about the future of physics itself. Black holes are the universe's ultimate pressure cookers, places where matter gets crushed so densely, even light can't escape. Yet their crushing grip pales in comparison to the Planck Epoch's extremes. Inside a black hole's core, matter collapses into a singularity, reaching densities that make neutron stars look fluffy. But during the Planck Epoch, the entire universe was packed into a space far smaller than an atom, with densities so high they redefined the word extreme. Imagine compressing Mount Everest into a grain of sand, now shrink it another trillion times. That's Planck density, where spacetime itself begins to writhe like a stormy sea. Both black holes and the Planck Epoch force physics to its breaking point, but in revealingly different ways. A black hole's singularity is hidden behind an event horizon, its secrets locked away. The Planck Epoch, though, was a naked singularity, a moment when the whole cosmos existed without barriers, without shadows. This is why scientists obsess over black holes. They're the closest thing we have to a time machine for glimpsing those first chaotic moments. When matter falls into a black hole, it's stretched and scrambled in ways that might echo the quantum turbulence of the Planck Epoch. Enter Hawking radiation, the slow leak of energy from black holes predicted by Stephen Hawking. It's a quantum whisper in gravity's fortress, proving that even black holes aren't eternal. Particles and antiparticles flicker into existence at the event horizon, with one falling in and the other escaping. This dance of creation and destruction hints at something profound. Quantum effects alter gravity's rules, and if they can bend physics at a black hole's edge, they might also hold the key to understanding the Planck Epoch's quantum foam, a froth of spacetime bubbles popping in and out of existence at the smallest scales. Quantum foam is what happens when you zoom in on spacetime until it's no longer smooth, but a seething chaos of virtual particles and wormholes. It's like looking at calm ocean waves from a distance, only to realize they're actually a frenzy of colliding droplets up close. During the Planck Epoch, this foam wasn't just a microscopic curiosity, it was the fabric of reality. Black holes, with their ability to warp spacetime into knots, might be our best clue for testing this theory. If we could probe a black hole's core, we might catch spacetime itself dissolving into foam, mirroring the universe's first trillionth of a second. What ties these ideas together is a radical notion. Black holes aren't just cosmic dead ends. They're windows. When matter crosses the event horizon, it doesn't vanish, it presses against the same Planck scale physics that shaped the Big Bang. Some theories even suggest black holes could spawn new universes inside them, their crushing densities triggering a new inflationary epoch. It's a dizzying thought. Our universe might owe its existence to a black hole in some distant parent cosmos, just as future universes could blossom from the ones we see today. The Planck Epoch and black holes aren't just bookends of cosmic history. They're proof that the universe's wildest extremes are always connected, bound by the same quantum secrets. The cosmic microwave background isn't just a faint glow, it's a time capsule carrying snapshots of the universe when it was just 380,000 years old. But hidden within its subtle temperature variations lie echoes of something far older, the Planck Epoch. These whisper-thin anisotropies, slight fluctuations in the CMB's heat aren't random noise. They're cosmic hieroglyphs imprinted when the universe was a seething quantum foam, smaller than a proton. To understand how, picture a frozen pond in winter. The cracks in the ice don't form randomly. They trace the stresses and strains from when the water first froze. Similarly, the CMB's hot and cold spots reflect quantum jitters from the Planck scale, stretched to cosmic proportions during inflation. What began as subatomic ripples, fluctuations in energy so tiny they'd make an atom look like a galaxy, became the gravitational seeds for everything. Galaxy clusters now sit where these ancient wrinkles were slightly denser, their gravity pulling matter together over billions of years. The precision of these measurements is staggering. Satellites like Planck have mapped the CMB's temperature to within 1 part in 100,000, revealing patterns so consistent they couldn't be accidental. The hottest spots, they correspond to regions where space itself stretched a fraction more during inflation, driven by quantum turbulence in the Planck Epoch. The coldest, where spacetime stretched slightly less. It's as if the universe kept a meticulous diary of its first moments, written in degrees above absolute zero. But the CMB doesn't just hint at the Planck Epoch's chaos, it challenges our theories. The statistical distribution of these anisotropies matches predictions from quantum physics eerily well, yet there are anomalies. Large-scale patterns in the CMB appear unexpectedly lopsided, as if the universe had a preferred direction in its infancy. Some researchers speculate this could trace back to asymmetries in the Planck scale quantum foam, while others propose it's evidence of a pre-Big Bang universe brushing against ours. Most tantalizing are the CMB's polarization patterns, subtle swirls in the light's orientation caused by gravitational waves from inflation. If these waves originated in the Planck Epoch, when gravity was merging with quantum forces, they'd carry fingerprints from that unification. Future telescopes hunting these signals might finally answer whether spacetime is fundamentally grainy or if extra dimensions left their mark. What's breathtaking is how much we've decoded from what seems like static. The CMB is more than a relic. It's a Rosetta Stone, translating quantum whispers from the universe's first heartbeat into a language we can almost understand. And with every new observation, we're not just studying the past, we're peering into the Planck Epoch's shadow, where the rules of reality were still being written. There's a reason the Planck Epoch remains one of physics' most tantalizing mysteries. Our current theories, as powerful as they are, hit a wall when confronted with those first moments. General relativity, Einstein's masterpiece, beautifully explains the dance of planets and the bending of light around black holes. Yet in the Planck Epoch's extreme heat and density, its equations dissolve into infinities, like a calculator throwing up error messages when pushed beyond its limits. Similarly, quantum mechanics, which thrives in the subatomic world, can't handle gravity's overwhelming presence in that primordial chaos. It's as if we've been given two flawless languages, one for the cosmos, one for the quantum, but neither can translate the universe's first words. This isn't just a minor gap in our understanding, it's a chasm. Picture trying to assemble a puzzle where half the pieces are from a different box. Relativity treats spacetime as a smooth, continuous fabric, warped by mass and energy. Quantum mechanics insists everything is discrete, grainy, governed by probabilities. Both work brilliantly in their respective domains, but in the Planck Epoch, where the universe was smaller than an atom yet hotter than a star, these frameworks clash violently. Gravity, which curves spacetime in relativity, should theoretically behave like a quantum particle at these scales, a so-called graviton. But no one's ever detected one, and the math to describe it remains elusive. The heart of the problem lies in the concept of measurement itself. Quantum mechanics relies on probabilities where particles exist in fuzzy superpositions until observed. But how do you observe the entire universe when there's nothing outside it to take the measurement? Even time, which ticks predictably in relativity, becomes fluid and uncertain at Planck scales. Some theories suggest time might not have existed at all in those earliest moments, emerging only as the universe cooled. Imagine baking a cake without a timer, where the recipe itself creates the concept of minutes. That's the level of paradox physicists wrestle with. Efforts to bridge this divide have spawned some of science's most ambitious ideas. String theory imagines vibrating filaments of energy as the fundamental building blocks, while loop quantum gravity proposes spacetime is woven from interlocking loops. Yet neither has been proven, and both remain mathematically dense, lacking experimental proof. Even the holographic principle, the notion that our three-dimensional universe might be a projection of information stored on a two-dimensional surface, stems from this desperation to reconcile the irreconcilable. What makes this so frustrating is that the Planck Epoch isn't some abstract curiosity. It's the foundation, the universe's expansion, the dominance of matter over antimatter, even the arrow of time. They all trace back to decisions made in that trillionth of a second. Without a theory of quantum gravity, we're like historians trying to write the story of civilization without knowing how fire was discovered. Every observation, from the spin of black holes to the afterglow of the Big Bang, hints at a deeper layer of reality we can't yet access. This isn't just a technical challenge, it's a philosophical reckoning. Physics has always thrived on reductionism, breaking complex systems into simpler parts. But the Planck Epoch resists this approach. Here, the universe wasn't a collection of separate forces and particles. It was an undivided whole where every interaction was entangled with every other. To understand it, we might need more than new math. We might need a new way of thinking, one that embraces the chaos of beginnings rather than forcing it into categories born from a cooler, calmer cosmos. For now, the Planck Epoch remains a mirror reflecting the limits of our knowledge. every time we probe deeper into black holes or simulate the early universe on supercomputers, we're not just searching for answers. We're confronting the humbling truth that some mysteries refuse to fit neatly into our models. And perhaps that's the most important lesson of all. The universe's first moments weren't just a physical transformation. They were a reminder that reality, at its core, is far stranger than we've dared to imagine. To recreate the Planck Epoch in a lab, we'd need a machine capable of generating energies so colossal. They defy imagination, roughly 10 trillion times more powerful than what our most advanced particle colliders can achieve. The Large Hadron Collider, humanity's most impressive physics experiment, smashes protons together at 99.9999% the speed of light. Yet even these violent collisions only scratch the surface of what existed during the universe's first trillionth of a second. It's like trying to reconstruct the birth of a hurricane by blowing on a teacup. The challenge isn't just about raw power, it's about scale. To probe Planck-length distances, you'd need particles with wavelengths smaller than an atom's nucleus by a factor of 10 to the power of 20. That's equivalent to trying to detect a single grain of sand on Mars using a telescope from Earth. Current detectors simply can't resolve phenomena at these extremes. Worse still, the very particles we'd need to accelerate would be so energetic, they'd immediately collapse into microscopic black holes under their own gravity, evaporating before we could study them. Cosmic observations don't fare much better. While telescopes like Hubble and JWST peer billions of years into the past, the Planck Epoch remains veiled behind an impenetrable curtain. The cosmic microwave background only emerges 380,000 years after the Big Bang. It's like trying to guess the ingredients of a baked cake by only examining the crumbs left on a plate. Some theorists propose looking for indirect signatures, subtle imprints in gravitational waves or anomalies in quantum entanglement that might carry echoes of Planck-scale physics. Others suggest harnessing extreme astrophysical events like neutron star collisions or primordial black holes as natural laboratories. But these approaches remain speculative, like trying to reconstruct a symphony from hearing only its faintest reverberations through concrete walls. What makes this so frustrating is that the answers likely exist etched into the fabric of reality itself. The universe remembers its origins, but we lack the tools to interrogate it properly. Until technology catches up with theory, the Planck Epoch remains both our greatest mystery and our most compelling frontier, taunting us with questions just beyond our grasp. If the Planck Epoch was a storm, Planckians would be the raindrops hypothetical particles so small they make quarks look like boulders. These aren't just any theoretical constructs, they're the universe's potential building blocks at the smallest conceivable scale, where space and time lose all semblance of order. Picture this: a single Planckian would be to a proton what a proton is to the entire solar system. That's how vanishingly tiny we're talking. But their size isn't what makes them extraordinary. It's their role in stitching together the fabric of reality when gravity and quantum forces were indistinguishable. The math behind Planckians is as elegant as it is mind-bending. According to quantum gravity theories, these particles would carry energy equivalent to the Planck scale, 10 to the power of 19 gigaelectronvolts, a number so large it dwarfs anything our particle colliders can produce. Their mass roughly 20 micrograms, which sounds trivial until you realize that's concentrated into a volume a billion trillion times smaller than an atom. Packing that much mass into that infinitesimal space would warp spacetime itself, creating fleeting quantum black holes that pop in and out of existence like bubbles in boiling water. Why do physicists entertain such wild ideas? Because Planckians could solve the singularity problem. If these particles existed during the Planck Epoch, they might have prevented the infinite densities predicted by classical physics, acting as nature's ultimate shock absorbers. Think of them as cosmic pixelation. When you zoom in too far on a digital image, you hit indivisible pixels. Planckians could be spacetime's pixels, ensuring the universe never quite reaches true infinity. Some models even suggest they mediated the unified superforce, transforming from one type of particle to another as the universe cooled and forces split apart. The catch: Planckians are ghosts in the machine. No experiment has ever detected them, and we lack the technology to probe such extreme energies directly. Yet their fingerprints might linger in subtle ways. If spacetime is indeed granular at Planck scales, high-energy cosmic rays could interact with this quantum foam, leaving telltale signatures in their travel patterns. Gravitational wave telescopes might one day catch echoes of Planckian activity in the ripples from black hole collisions. What's fascinating is how these speculations blur the line between particle physics and cosmology. Planckians aren't just relics of the past, they could be everywhere, woven into the vacuum of space itself. Every time a quantum fluctuation creates a virtual particle, it might briefly tap into the same primordial physics that birthed them. In this way, the Planck Epoch isn't a distant memory. It's a layer of reality we're only beginning to uncover, hidden in plain sight. One of the most radical ideas in modern physics suggests that everything we perceive as three-dimensional might actually be a projection, like a cosmic hologram. The holographic principle flips our intuition inside out by proposing that the universe's entire information content, from swirling galaxies to the neurons firing in your brain, could be encoded on a two-dimensional surface at its boundaries. If this sounds like science fiction, consider the math. Black holes, those ultimate destroyers of information, might actually preserve it on their event horizons, scrambled into microscopic pixels. Now stretch that idea back to the Planck Epoch, when the entire observable universe was smaller than a single atom. Suddenly, the holographic principle isn't just theoretical, it's a survival guide for reality's earliest moments. Here's why this matters. During the Planck Epoch, the universe was so unimaginably dense that spacetime itself was likely a seething quantum foam, bubbling with virtual black holes and wormholes. Traditional physics crumbles at these extremes, but the holographic principle offers a lifeline. If the cosmos can store its information on a 2D surface, then the chaotic 3D mess of the early universe might have had an underlying order, a hidden code etched into the fabric of reality. Think of it like a Blu-ray disc. The vivid, three-dimensional movie you watch is actually stored as flat, two-dimensional data. Similarly, the universe's apparent complexity could emerge from a simpler, lower-dimensional blueprint. Black holes are the key to this puzzle. When matter falls into a black hole, it doesn't just vanish. According to the holographic principle, its information gets smeared across the event horizon like ink on a stretched balloon. This isn't just poetry, it's thermodynamics. Just as heat disperses in a gas, information disperses on a horizon, preserving the universe's total data budget. Now rewind to the Planck Epoch, when the entire cosmos was as energy-dense as a black hole's interior. The same logic applies. The universe's information might have been plastered across its own cosmic horizon, a boundary we can no longer see but whose fingerprints linger in the way quantum fields and gravity interact. The implications are staggering. If the holographic principle held sway during the Planck Epoch, it could explain why our universe seems finely tuned for life. The 2D code might have acted like a cosmic constraint, preventing the early universe from collapsing into chaos or ripping itself apart. It's as if reality had guardrails, ensuring that no matter how wildly the quantum foam bubbled, the underlying information stayed coherent. This could also resolve the infamous black hole information paradox, the idea that black holes erase information, violating quantum mechanics. If information is always preserved on surfaces, then nothing is ever truly lost, just transformed. Critics argue the holographic principle remains untested, and they're right. We lack the tools to experimentally probe Planck-scale physics or black hole interiors. Yet indirect evidence is mounting. simulations of quantum gravity models often produce holographic behavior spontaneously, like a 3D image emerging from 2D rules. Even the cosmic microwave background's fluctuations, those faint echoes of the Big Bang, show patterns that some theorists argue mirror holographic projections. What's breathtaking is how this idea connects the universe's birth to its eventual fate. Black holes might eventually evaporate, their information leaking away as Hawking radiation. But if the holographic principle is true, that information was never truly inside them to begin with. It was always on the surface, waiting to be decoded. Similarly, the Planck Epoch's chaos wasn't lawless. It was a dance of information, a primal algorithm running on the spacetime equivalent of a quantum hard drive. And if that's the case, then the universe isn't just a place. It's a story written in light, gravity, and entropy, with its opening lines inscribed in 2 dimensions during that first trillionth of a second. While string theory dances with extra dimensions and vibrating strings, loop quantum gravity takes a radically different approach. It rewrites the fabric of spacetime itself. Imagine the universe not as a smooth, continuous sheet, as Einstein envisioned, but as a tapestry woven from tiny, indivisible stitches. These are the atoms of spacetime, each no larger than a Planck length, forming a network of interconnected loops that give reality its structure. It's like zooming in on a piece of fabric until you see the individual threads, realizing what looked seamless is actually a meticulous weave. This isn't just poetic imagery, it's a mathematical revolution. In loop quantum gravity, space isn't infinitely divisible. It's granular with a finite smallest possible size. Time, too, ticks in discrete steps like frames in a cosmic film reel. During the Planck Epoch, when the universe was smaller than one of these spacetime atoms, the very concepts of before and after may have blurred. Gravity, instead of curving a smooth continuum, would have arisen from the twists and knots in this quantum weave. Picture a mesh of invisible rubber bands stretching and tangling as the universe expanded, each loop carrying a quantum of area or volume resisting infinite compression. What sets this apart from string theory? No extra dimensions, no vibrating strings, just pure geometry. While string theory unifies forces by adding complexity, loop quantum gravity simplifies by reducing reality to its most basic building blocks. The equations describe how these loops interact, creating spacetime's dynamism from the ground up. When applied to the Planck Epoch, the model suggests a breathtaking possibility. The Big Bang might not have been a singularity at all, but a big bounce. As a previous universe collapsed, spacetime's granularity would have prevented total collapse, rebounding into our expanding cosmos like a quantum trampoline. Evidence for this lies in black holes. Loop quantum gravity predicts that inside a black hole's core, spacetime doesn't crush to infinity. It undergoes a quantum phase transition, potentially birthing a new universe. This echoes the Planck Epoch's conditions, where the same quantum geometry would have governed reality's rebirth. The theory also resolves the problem of time's arrow. With discrete time steps, the early universe's chaos wasn't random noise but a structured cascade of quantum loops falling into place. Yet challenges remain. Unlike string theory's elegance, loop quantum gravity's math is notoriously complex, and it struggles to explain how smooth spacetime emerges from such jagged foundations. But its power lies in its honesty. It doesn't shy from the Planck Epoch's quantum weirdness. It embraces the chaos, offering a universe where spacetime itself is born from entanglement, where the past and future are stitched together by loops too small to see, but whose patterns shape everything from galaxies to the thoughts in your brain. The Planck Epoch wasn't just the birthplace of our universe, it might have been the nursery for countless others. Some of the boldest theories in cosmology suggest that quantum fluctuations in those first moments didn't just shape our cosmos, but spawned entire alternate realities, each with its own unique physics. Picture a pot of vigorously boiling water where bubbles constantly form and burst. Now imagine those bubbles aren't made of vapor, but entire universes, some where gravity is stronger, others where time runs backward, and a rare few where conditions allow life like ours to emerge. This is the multiverse hypothesis, and its roots stretch all the way back to that first trillionth of a second. During the Planck Epoch's quantum chaos, spacetime itself was subject to wild, probabilistic fluctuations. Most smoothed out as inflation progressed, but some models suggest certain fluctuations could have grown large enough to pinch off into self-contained universes. It's like shaking a snow globe so violently that droplets escape, except here, the droplets are entire cosmic realities. These baby universes would inherit random properties from their parent, meaning some might have 5 fundamental forces instead of 4, or 7 spatial dimensions rather than 3. The implications are staggering. Our universe's precise tuning for life might not be special at all, just one possible outcome in an endless cosmic lottery. Inflation theory lends credence to this idea. Just as our universe underwent exponential expansion, other regions of quantum foam might have inflated at different rates, creating isolated, bubble universes within a grander multiverse. Some bubbles would instantly collapse, others might expand forever. The key insight: these bubbles wouldn't exist somewhere else in our space. They'd occupy entirely separate spacetime fabrics, like non-overlapping ripples in a pond. This explains why we'll never detect them directly, but their existence could resolve puzzling features of our own cosmos, like the inexplicably low energy of empty space. String theory adds another layer to the multiverse concept. The math suggests there could be 10 to the power of 500 possible vacuum states, each representing a unique universe with different particle properties and physical laws. During the Planck Epoch, quantum turbulence might have randomly selected one configuration for our universe while others branched off. Think of it as a cosmic game of roulette where every possible outcome actually occurs somewhere in the multiverse. This isn't pure speculation. Strange anomalies in our universe hint at possible collisions with neighboring bubbles, suggestions of cold spots in the cosmic microwave background, or unexpected correlations in galaxy distributions. While inconclusive, these clues keep the multiverse hypothesis alive. More fundamentally, the idea reframes the Planck Epoch's significance, no longer just our origin story, but potentially the moment when reality itself diversified into infinite variations. What began as quantum jitters in an ultra-dense speck might have spawned a reality far stranger than we ever imagined. Dark matter and dark energy, those mysterious forces shaping the cosmos, might not be latecomers to the universe's story. Their origins could stretch all the way back to the Planck Epoch, buried in the chaos of that first trillionth of a second. Think of the early universe as a sculptor's workshop, where the fundamental ingredients of reality were still cooling into place. In that frenzied moment, hidden structures could have formed structures we now perceive only through their gravitational shadows. Consider dark matter first. Today, it silently threads through galaxies, holding them together with its invisible grip. But what if it's not some exotic particle we've yet to discover? What if it's a relic from the Planck Epoch, a frozen remnant of that primordial superforce? When gravity and the other forces were still unified, quantum fluctuations might have birthed dense knots of energy like cosmic fossils that decoupled as the universe expanded. These knots, impervious to light but warping spacetime itself, could be the dark matter we've been chasing. It's as if the universe's first moments left behind an invisible scaffold, and galaxies simply grew around it. Then there's dark energy, the enigmatic force accelerating the universe's expansion. While it dominates today, its roots might lie in the Planck Epoch's vacuum energy, a seething, unstable ocean that briefly flooded the cosmos before inflation diluted it. But traces could have lingered, woven into the fabric of spacetime. As the universe stretched, this latent energy might have reawakened, pushing galaxies apart like an unstoppable tide. Some theories even suggest dark energy isn't constant, that it's a dynamic field echoing the Planck Epoch's quantum turbulence, its strength fluctuating over cosmic time. The beauty of this idea is how elegantly it ties together two of cosmology's biggest puzzles. Dark matter and dark energy aren't random anomalies, they could be cosmic breadcrumbs leading us back to the universe's first heartbeat. If true, studying them today is like eavesdropping on a conversation that began 13.8 billion years ago, when the rules of reality were still being written. One thing's certain, the Planck Epoch didn't just set the stage for the universe we know. It might have left behind clues in the very darkness we're still struggling to illuminate. Time moves forward, that's one of the most fundamental truths of our existence. Eggs crack but never uncrack, coffee cools but never reheats itself, memories accumulate but never reverse. This relentless one-way flow is called the arrow of time, and its origins might trace back to the Planck Epoch. But why does time have a direction at all? The answer could lie in entropy, the universe's tendency toward disorder, and its bizarrely low starting point in those first fleeting moments. Picture a deck of cards fresh from the factory, perfectly ordered by suit and number. Shuffle it once and it's slightly disordered. Keep shuffling and chaos takes over. The universe works the same way, from order to disorder, never the reverse. But here's the puzzle. Why was the early universe so ordered to begin with? During the Planck Epoch, the cosmos was a seething, high-energy soup, yet its entropy was paradoxically low. It's like opening a new deck only to find the cards already scattered, except in this case they were stacked too perfectly. That initial low entropy state set the stage for everything that followed, like a wound-up spring slowly unwinding across billions of years. Quantum fluctuations in the Planck Epoch might hold the key. In that chaotic froth of spacetime, tiny, random variations could have carved out pockets of unexpected order. Some theories suggest these fluctuations didn't just influence the distribution of matter, they set the initial conditions for entropy itself. Imagine a vast ocean with waves crashing in all directions, but one tiny region where the water inexplicably calms. That fleeting moment of calm could have been enough to anchor time's arrow, giving it a direction to follow as the universe expanded. The link between entropy and time isn't just philosophical, it's written into the laws of physics. The second law of thermodynamics states that entropy always increases, creating an irreversible flow. But without that initial low entropy state, time wouldn't have a clear forward direction. It's as if the Planck Epoch handed the universe a loaded die, waited to roll toward disorder. Some physicists argue this wasn't an accident. The holographic principle suggests that information packed onto a 2D surface during the Planck Epoch could have enforced an entropy gradient, like a cosmic ramp sloping only one way. Black holes add another layer to the mystery. They're entropy powerhouses with event horizons acting as ultimate one-way doors. Matter falls in, but nothing escapes, a perfect metaphor for time's irreversibility. If black holes preserve information on their surfaces, as the holographic principle suggests, then the Planck Epoch might have worked similarly, encoding entropy's starting point in the geometry of spacetime itself. The universe didn't just have low entropy, it was programmed to unleash it slowly, like a timed cosmic clockwork. What's fascinating is how fragile this setup might have been. If the Planck Epoch's quantum fluctuations had tilted slightly differently, entropy could have started higher, leaving no clear arrow of time. Causality might have blurred with effects preceding causes. Stars could have formed and dissolved at random. Life reliant on orderly chemical reactions would have been impossible. The fact that we exist to ponder these questions hints at something profound. The Planck Epoch didn't just set the stage. It wrote the script for time itself. Some theories go even further, proposing that the arrow of time isn't unique to our universe. In a multiverse scenario, other bubble universes might have arrows pointing in different directions, their entropy gradients locked in during their own Planck-like beginnings. Ours just happens to align with the emergence of complexity, of galaxies, of consciousness. It's a humbling thought. The reason we remember the past but not the future might stem from quantum ripples in a universe smaller than a proton over 13 billion years ago. The Planck Epoch's grip on time doesn't stop there. Even the perceived flow of time, the sensation of moments passing, might trace back to those initial conditions. In loop quantum gravity, spacetime's granular structure means time doesn't truly flow smoothly but advances in discrete jumps like frames in a movie. During the Planck Epoch, these jumps were unimaginably rapid, creating a kind of primordial rhythm that still underlies reality. Our experience of time as continuous could be an illusion, a cosmic holdover from when the universe's clock first started ticking. So the next time you watch steam rise from your coffee or notice a new wrinkle in the mirror, remember, those everyday signs of time's passage aren't just local phenomena. They're echoes of the Planck Epoch reverberating across eternity. The universe could have been timeless, directionless, a static loop of events without before or after. Instead, it chose a path, and we're riding that arrow all the way from the Big Bang to whatever comes next. The Planck Epoch doesn't just challenge physics, it shatters our most basic assumptions about existence. If time and space as we know them flickered into being during that first trillionth of a second, what does that mean for the concept of a beginning? We're forced to confront the unnerving possibility that before might not just be unknown, it might be meaningless. Think of it like asking what's north of the North Pole. The question itself might be flawed because time, as we experience it, could be a product of the universe, not a container it sits inside. This leads to one of the most profound riddles in cosmology. How did everything emerge from what appears to be nothing? The word nothing here is deceptive. Quantum mechanics tells us that even a perfect vacuum seethes with potential virtual particles blinking in and out of existence, borrowing energy from nowhere. In the Planck Epoch, this quantum frenzy wasn't confined to a vacuum. It was the vacuum. The universe's entire energy budget might have balanced to zero, with positive mass energy cancelled out by negative gravitational energy. In this light, nothing becomes a misnomer. The cosmos could be the ultimate free lunch, a fluctuation in a deeper, timeless reality where the distinction between something and nothing dissolves. Some philosophers and physicists argue that the Planck Epoch hints at a cyclical universe, where big bangs and big crunches repeat like cosmic seasons. Others propose a multiverse, where our universe is one bubble in an infinite froth of possibilities. But these theories only push the mystery one step back. Even an eternal multiverse needs a substrate, a rulebook for how bubbles form. The deeper we dig, the more we're left with a choice: accept brute facts about existence or admit that our language, words like cause and beginning, might be too small to hold the truth. The human mind craves narratives. We want origins and endpoints, but the Planck Epoch resists storytelling. It's a reminder that reality, at its core, might not care about the frameworks we invent to make sense of it. This isn't just a scientific challenge, it's an existential tremor. If the universe didn't start in any conventional sense, what does that say about our place in it? Are we transient patterns in a cosmic process too alien to name? Or is consciousness itself a clue, a way for the universe to reflect on its own origins? These questions don't have answers yet, and that's precisely what makes them electrifying. The Planck Epoch isn't just a chapter in a physics textbook, it's a mirror held up to the limits of human understanding. Every time we peer into its depths, we're not just studying the past. We're confronting the mystery of why there's a we to study anything at all. Stephen Hawking reshaped our understanding of the universe's birth by tackling its most paradoxical edge, the moment before time began. While most physicists avoided the singularities' infinite absurdities, Hawking pivoted, asking a revolutionary question: what if there was no boundary at all? His no-boundary proposal reimagined the Big Bang not as an explosion from nothing, but as a smooth geometric curve, like the rounded tip of a pear where the stem represents time's emergence. No sharp edges, no infinities, just a seamless transition from quantum fuzz to cosmic dawn. This idea sprang from Hawking's work with physicist James Hartle, blending quantum mechanics with relativity in a daring mathematical waltz. They treated the early universe like a quantum particle existing in a superposition of possible states, each with its own spacetime geometry. In this view, the Planck Epoch wasn't a singular point but a probabilistic smear where before and after lost meaning. Picture a snow globe shaken so violently that the flakes freeze midair. Hawking's model suggests time itself crystallized from such quantum turbulence with no definitive starting line. The brilliance of the no-boundary proposal lies in its elegance. By abolishing the singularity, Hawking sidestepped the infinite densities that crippled earlier theories. Instead, he proposed a finite but boundless universe analogous to Earth's surface. You can travel endlessly without hitting an edge, yet the planet's volume remains finite. Similarly, Hawking's universe has no before the Big Bang because time, like latitude at the North Pole, simply folds into itself. This isn't just poetic imagery, it's mathematically precise, using imaginary time, a quantum concept where time behaves like space, to smooth the cosmic birth into a calculable event. Critics argue the model's reliance on imaginary time makes it untestable, a charge Hawking readily acknowledged, yet its implications ripple through modern cosmology. If correct, the no-boundary proposal implies the universe didn't begin. In a conventional sense, it transitioned like water freezing into ice. This reshapes our search for quantum gravity, suggesting spacetime's fabric might retain a memory of its pre-geometric past. Recent simulations of loop quantum cosmology even show bouncing universes that echo Hawking's geometry, hinting he might have glimpsed a deeper truth. Hawking's legacy here is twofold. He didn't just offer a technical fix, he reframed how we conceive of origins. By erasing the Big Bang's boundary, he turned cosmology's most intractable problem into a question of geometry, one where the universe in its purest form might not need a starting point at all. It just is eternally redefining itself. That shift, more than any equation, is his gift to science, the courage to imagine a universe without edges where even time bows to quantum possibility. Roger Penrose's vision of the cosmos isn't just revolutionary, it's poetic. While most theories treat the universe's birth and death as separate events, Penrose sees them as part of an endless dance. His conformal cyclic cosmology proposes something startling. The universe doesn't have a true beginning or end. Instead, it cycles eternally, with the infinitely remote future of one era blending seamlessly into the Planck Epoch of the next. Picture a cosmic phoenix where death and rebirth are the same moment, a universe so stretched and faded in its old age that it becomes indistinguishable from a newborn one. At the heart of this idea lies a mathematical sleight of hand. Penrose uses a concept called conformal rescaling, a way to stretch or shrink spacetime while preserving its angles. In the far future, when black holes have evaporated and particles have decayed into faint radiation, the universe becomes cold, vast, and nearly empty. Stretch this desolate landscape mathematically, and it starts to resemble the ultra-dense, ultra-hot singularity of the Big Bang. The two extremes, the ashes of one cycle and the fire of the next, become mirror images. This isn't just philosophy, it's geometry with consequences. The implications are staggering. If Penrose is right, the Planck Epoch wasn't a one-time event. It's a recurring phase, a cosmic reset button pressed every trillion years. Even more radical is his claim that traces of past universes might linger in ours. He points to mysterious Hawking points in the cosmic microwave background, circular patches of temperature variation that could be the faint imprints of ancient black holes from a previous cycle. These anomalies, if confirmed, would be like finding fingerprints on a newborn's hands, evidence of a life before birth. Critics argue that conformal cyclic cosmology stretches physics to its breaking point. How can information cross the gap between cycles? What mechanism ensures the laws of physics reset identically each time? Penrose's answer leans on quantum gravity's quirks, suggesting that at the crossover point, particles lose all sense of scale, forgetting their past as they're reborn. It's as if the universe suffers a selective amnesia, remembering only its geometric essence while discarding the details. What makes this theory so compelling is how it reframes time. Instead of a linear march from Big Bang to heat death, time becomes a loop, not in the cliched everything repeats sense, but in a deeper structural way. The universe's death isn't an end, it's a transformation, like ice melting back into water to freeze again. And if Penrose is correct, we're not just stardust, we're echoes of a cycle older than time itself, with the Planck Epoch as the hinge between each act of an endless cosmic play. The Planck Epoch remains tantalizingly out of reach, locked behind energies and scales our current technology can't touch. But the next generation of breakthroughs might finally crack the code, not by recreating those primordial conditions directly, but by uncovering subtle fingerprints they left behind. Quantum computers could simulate Planck-scale physics in ways classical machines never can, acting as digital time machines to model the universe's first murmurs. Unlike today's noisy intermediate-scale devices, future error-corrected quantum systems might handle the mind-bending math of quantum gravity, probing how spacetime itself emerged from chaos. Picture this, a quantum processor running a simulation where gravity and quantum forces intertwine, revealing patterns that match anomalies in cosmic microwave background data. That's the kind of indirect evidence that could bridge theory and observation. Meanwhile, telescopes are evolving into cosmic historians. The next wave of gravitational wave detectors, like the planned Laser Interferometer Space Antenna, could catch echoes from inflation ripples in spacetime so ancient they might carry imprints of Planck-scale fluctuations. Even more ambitious are proposals for quantum telescopes, leveraging entanglement to peer beyond the cosmic microwave background's veil, potentially glimpsing residual signals from the universe's infancy. It's like trying to reconstruct a symphony from the vibrations it left in the walls of a concert hall billions of years later. The real magic happens when theorists and experimentalists collide. String theorists crunch equations predicting higher dimensional resonances, while particle physicists scour Large Hadron Collider data for exotic particles that might hint at those dimensions. Cosmologists map the universe's large-scale structure, searching for anomalies that loop quantum gravity models forecast. This isn't just interdisciplinary work, it's a collective detective story where each clue, whether from a lab or a telescope, reshapes our understanding of reality's foundations. What's exhilarating is how these tools complement each other. Quantum simulations might suggest where to point telescopes, while unexpected telescope data could inspire new quantum algorithms. The Planck Epoch's secrets won't surrender to a single approach. They'll emerge from the interplay of human ingenuity, a reminder that the universe's deepest mysteries are puzzles best solved together. The Planck Epoch's mind-bending physics hasn't just captivated scientists, it's fueled the imaginations of storytellers, turning quantum chaos into gripping sci-fi. From time loops to multiverse mayhem, the era's unresolved mysteries offer a playground for fiction where the rules of reality bend to the whims of narrative. Take Christopher Nolan's Tenet, where entropy reversal mirrors theories of Planck-scale thermodynamics, or Doctor Who's Reboot, weaving the Big Bang into a poetic reset of the universe. These aren't just artistic liberties, they're creative extrapolations of real cosmological dilemmas. What if time's arrow wasn't fixed? What if the universe remembered its origins? Video games like No Man's Sky lean into the Planck Epoch's generative potential, offering procedurally generated galaxies that echo the quantum fluctuations of the early cosmos. Each player's unique universe springs from algorithmic seeds, much like our own reality may have crystallized from primordial randomness. Meanwhile, the Outer Wilds crafts a poetic metaphor for cyclic cosmology, with a solar system trapped in a time loop that resets upon death, a nod to theories like Penrose's conformal cycles, where the end of one universe births another. The game's haunting finale even hints at quantum observers shaping reality, a playful riff on the role of consciousness in cosmological models. Literature digs deeper. Greg Egan's Diaspora imagines post-human civilizations surviving the Planck Epoch's extremes by encoding themselves into Planck-scale quantum foam, while Lou Sixon's The Three-Body Problem trilogy wages cosmic war by weaponizing fundamental physics, manipulating the very constants set during the universe's infancy. These stories resonate because they anchor their wildest ideas in real science, however loosely. When a Star Trek episode posits a Big Bang gun capable of rewriting space-time, it's not just technobabble, it's a pop culture echo of humanity's quest to decode the Planck Epoch's legacy. Even horror taps into the era's existential dread. Films like Annihilation and The Void depict reality unraveling at the edges, where biology and physics blur, an aesthetic cousin to the quantum foam's instability. The terror isn't just in the monsters, but in the implication. The universe's foundations might be fragile, a temporary order imposed on primordial chaos. It's a theme that traces back to Lovecraft's cosmic horror, updated with modern physics vocabulary. What unites these stories is their willingness to stare into the Planck Epoch's abyss and ask not just how, but what if. They take the dry equations of quantum gravity and spin them into myths for the modern age, where black holes become portals and the Big Bang a reset button. This cultural alchemy matters because it shapes how we collectively imagine the cosmos, not as static equations, but as a living, evolving mystery. Every sci-fi riff on alternate dimensions or time loops plants seeds for future scientists who might one day turn fiction into fact. After all, today's warp drives are tomorrow's engineering challenges. The Planck Epoch, for all its inscrutability, reminds us that reality's weirdest truths often outpace our wildest stories. One of the biggest myths about the Big Bang is that it was an explosion in space, like a cosmic firework bursting outward into some pre-existing emptiness. But here's the twist: space itself didn't exist before the Big Bang. There was no outside for the universe to expand into. Picture it like this: imagine a balloon covered in dots. As you blow it up, every dot moves away from every other dot, not because they're exploding outward from a center, but because the fabric of the balloon itself is stretching. The Big Bang wasn't matter flying through space. It was space itself unfurling, carrying matter along for the ride. Then there's the misconception that the Planck Epoch is something we could see if we had a powerful enough telescope. But the truth is far stranger. Light didn't even exist, yet photons wouldn't form until hundreds of thousands of years later. The Planck Epoch was more like a blindfolded sculptor shaping clay in absolute darkness. The universe was so dense that light couldn't travel freely, let alone escape to some future observer. Even if we built a telescope the size of a galaxy, we'd hit a hard wall. The cosmic microwave background, the oldest light we can detect, only reveals the universe after it cooled enough to become transparent. Some assume the Planck Epoch was just a hotter, denser version of today's universe, like squishing the cosmos into a tiny box, but the reality is far wilder. At those energies, the very concepts of particles or forces break down. It wasn't just a crowded room, it was a room where the walls, the floor, and the air were all the same chaotic stuff. Think of it like trying to describe a smoothie's ingredients after they've been blended into a single liquid. You can't point to the strawberry or the banana anymore, they've lost their identities entirely. Another persistent myth: that time flowed in the Planck Epoch the way it does now. In truth, time itself may have been more like a directionless quantum froth, bubbling without a clear before or after. It's like watching a pot of water about to boil. Individual bubbles pop unpredictably, lacking any orderly sequence. Only as the universe cooled did time crystallize into the steady arrow we know today, a rhythm emerging from chaos. Perhaps the most tempting misconception is that the Planck Epoch was the absolute beginning, but many physicists suspect it might have been a transition, a rebound from a previous universe or a quantum fluctuation in some deeper reality. Saying the Planck Epoch was the first moment might be like calling the first frame of a movie the entire story, ignoring the possibility of an unseen prologue. The universe doesn't owe us a tidy origin story, and the Planck Epoch's mysteries remind us that some answers might lie forever beyond the limits of human intuition. So the next time someone calls the Big Bang an explosion or claims we'll see the Planck Epoch with better tech, remember reality's first moments weren't just a scaled-down version of today's cosmos. They were a realm where the rules themselves were being forged, a place where our everyday language fails and only mathematics dares to whisper the truth. And that's the real wonder. The more we learn, the clearer it becomes that the universe's birth wasn't just strange, it was stranger than we can imagine. The Planck Epoch wasn't just the universe's first moment, it was its most radical act of reinvention. Everything we know, from the forces that bind atoms to the vast cosmic web of galaxies, traces back to that fleeting trillionth of a second when reality was raw, unformed, and teeming with possibilities. This wasn't merely the dawn of time, it was the frontier where physics as we know it dissolves into quantum chaos, where gravity and light were fused into a single superforce, and where spacetime itself flickered into existence like a candle in the dark. What makes this era so endlessly fascinating isn't just its extreme conditions, it's the unanswered questions it leaves hanging. Why does our universe have the precise mix of forces and constants that allow stars, planets, and life to exist? Was the Planck Epoch truly the beginning, or just a turning point in an eternal cycle? And how do we reconcile the smooth cosmos we see today with the seething quantum foam that birthed it? These aren't just academic puzzles, they're clues to the deepest nature of reality. Yet for all its mystery, the Planck Epoch isn't some distant abstraction. Its fingerprints are everywhere, the galaxies spinning at the edge of telescopes, the dark energy accelerating the universe's expansion, even the arrow of time guiding every moment. They all carry echoes of that primordial chaos. Every breakthrough in quantum gravity, every new detection of gravitational waves, brings us closer to decoding those echoes. We're like detectives piecing together a cosmic crime scene where the clues are written in mathematics and the witnesses are particles older than stars. So where does that leave us? At the edge of understanding, peering into the abyss of the unknown? The Planck Epoch reminds us that science's greatest stories aren't just about answers, they're about learning how to ask better questions. And while we may never fully grasp what happened in that first heartbeat of existence, the pursuit itself transforms how we see the universe and our place within it. This isn't the end of the journey, it's just the beginning. From the enigma of dark energy to the quest for quantum gravity, the cosmos is brimming with secrets waiting to be uncovered. So stay curious, because the next revelation might not just change our textbooks, it could rewrite the very story of reality. And who knows, the next chapter might be closer than we think.